Um, so, you know, so we sort of started the semester talking about the foundations of quantum mechanics and thinking, trying to think about the way in which fundamentally quantum theory is different from classical theory. And some of it we just sort of threw up and said, threw up our hands, we didn't throw up. We might have wanted to. And said, well, you know, it's just the way it is. But in some sense, we haven't really gotten to the question, how do we know that this is the way it is? And what distinguishes really the kind of reality or lack thereof at the microscopic world from the classical world? What can we really say about this? So, you know, historically, as I think you probably know, Einstein was famously unhappy with what was called the new quantum theory. Now, you may know that Einstein won the Nobel Prize not for relativity, but for the photoelectric effect. And Einstein was involved in the early 20th century with the developments of modern physics and wave-particle duality and such things. But what was developed by Bohr and De Broglie and Schrödinger in what was called the new quantum theory, which was in the 1920s, 1930s, was a different kind of theory which involved sort of this notion of intrinsic randomness. Now, randomness, again, is not something that's unfamiliar. In fact, Einstein was one of the major contributors to statistical physics and thermodynamics, theory of Brownian motion. All of this really came from Einstein. So the idea that things were random wasn't the problem. It's how did we interpret that randomness? So what does it mean for something to be random when we have a random outcome? Well, the way in which we usually understand what it means for something to be random, that is to, well, so randomness means that the outcome of a measurement is not completely determined. So the question is, why is that? Well, typically we would say that there would be reasons for randomness, is that there's missing information. That's to say, we don't have a complete description of all the aspects of the system, you know, the famous, you know, which hand is the chalk in? Well, it's in neither because I dropped it. But you see, you didn't have that information. So, when we say there's missing information, another way of saying that is that there's a hidden variable that we don't know. Hidden variable or variables. If we knew everything, then it would be completely determined, okay? But quantum mechanics seems to say, talks about that somehow there's some kind of intrinsic randomness. where the complete description doesn't even exist. And it's, we don't even know what we're talking about, frankly, when we say that. I mean, this is the thing we continue to struggle with and why we continue to waffle when we talk about the foundations of quantum mechanics, because at some point we see something, and at what point does that something arise? I mean, you know, as we discussed at the very beginning of the semester, we have this kind of two kinds of evolution of the quantum state. One kind of evolution is deterministic, and one kind of evolution is this stochastic, or random evolution. And at what point do we even say that that's when the evolution happens randomly? We say when a measurement happens, but what constitutes a measurement? So Einstein just thought that this was nonsense. And but there must be, the reason that you see random events when you do measurements, that there is really a hidden variable. There's an incomplete description. Quantum mechanics we didn't have the complete description, and it could be completed if we just knew sort of what was under the hood. There's some hidden variables. Now there's one other important aspect of this, which is what we call local hidden variables. Now this is something that was kind of intrinsic to Einstein's thinking about hidden variables because, of course, he was the genius behind the idea of relativity, and that all events were communicated no faster than the speed of light, and everything happened locally and then was communicated no faster than the speed of light. There are descriptions of quantum mechanics that have hidden variables that are non-local. There's something known as the de Broglie-Bohm pilot wave theory, which we kind of talked about. We didn't really call it that, but when we talked about the decomposition of the wave function, as an amplitude and a phase, where we have this as the action, we wrote this at one point. There are descriptions of this which look like classical Hamilton-Jacobi theory of rays, but that was only in the geometric optic limit. If we had the wave optic limit, there was a more general description of how the trajectory moves, and there's a piece of it that has what's called the quantum potential. And it effectively, if you have many particles, is a non-local thing. So there are descriptions of quantum mechanics, at least in non-relativistic quantum mechanics without spin. Whether you can generalize that, they're very kind of crazy, and they're the advocates of the de Broglie-Bohm pilot wave theory. But fundamentally, the question you might ask is there a local hidden variable theory? As to say, there's something about this particle, I'm going to measure this particle, and I don't know everything about it because there are some hidden variables within it. And if I knew them, it would predict what's going to happen when I do that measurement. So in order to get at this and to sort of put a finer point on it, there's a famous paper from 1930 something, 1933, It's the Einstein, it's the Rosen paradox, or what we now call EPR. Or Podolsky and Rosen, I don't know who they are, but they get to be P and R, so they're not too bad for that. So they wanted to show that why it must be the case that the quantum mechanical description is incomplete, that there really were hidden variables. They wanted to provide a Gedanken experiment, a thought experiment, which forced you to conclude that quantum mechanics wasn't the full description of what was going on in the microscopic world, and it could be completed. Okay? So they wanted to have this idea of an element of reality. This is the terms that they used. And the way it's defined is the following. What they said is the following, quote, if, pardon me, without in any way disturbing the system, we can predict with certainty i.e. with unit probability the value of physical quantity then there exists an element of physical reality corresponding to that quantity. So let's try to parse that a little bit and think about what that is saying. What they want to get at the sense is when you do a measurement, what you're discovering is what the thing is objectively. It has some property, and when you look at it, you find out what it is. You didn't cause it to happen by the act of your measurement. It was real. It was objectively real, and you just found out what it was when you measured it, right? And they want to say that if you must grant me that that's the way the world is, if it's the case that the value you're going to see is 100% predictable. So if, with unit probability, you're going to find this result, then you must grant me that it had that value before you looked at it. Okay? So let's look at the example that they were given. So the way they got at this issue, and its paradoxical, has to do with entangled states. So the particular state, so entangled states, as we know, are quantum correlated multipartite, meaning multiple parts systems. you know, back in the day, there's, you know, this is the focus is on the uncertainty principle and position momentum. Okay, so instead of what EPR considered, what's now called the EPR state, is a particular state of correlation of position and momentum. So let me call the EPR state. I'll write it not in the way they wrote in their paper, but in some more modern language. So it's a bipartite system, two parts, A and B. There's particle A and there's particle B, okay? And they have, so they wrote down a state that's effectively this. Okay? So this is an entangled state. It's not a product state. It's a superposition. In fact, it's, in this case, a continuous superposition of product states, such that if you measure particle A, you will find it at position X. And if you measure particle B, you will find it at position X plus X naught. Yes, sir?
Are they eigenstates of position? Or
No, this is not an eigen, I mean, these are eigenstates of position.
Okay, but
It's a superposition of all of these,
okay.
right?
Okay.
If it was just this, that would be a product state.
Okay.
And then I definitely get this value X, but it's all possible, right? So so if I do a measurement and I find, let's say that this is 1 meter. X naught is 1 meter. If I find particle A here at the origin, then particle B is 1 meter away. If I find particle A over here at 0.2 meters, then I'll find particle B at 1.2 meters. Okay? So they're always correlated, they're always separated by exactly 1 meter. But I just don't know where I'm going to find A. A can be anywhere. B could be anywhere, but the distance between them is always exactly 1 meter. Okay? So if I measure particle A and I find it there, then instantaneously I know where particle B is. I know that particle B is exactly 1 meter away from where I found particle A. Yeah.
And you can tell the difference between A and B?
Yeah.
Okay, okay.
They need not be the same kind of particle. Okay? So this is an entangled state, it's correlated. Okay? This is an entangled state. There's a correlation between where particle A and particle B are. Where particle A is completely random, where particle B is completely random alone, but the correlation between them is deterministic. It's always exactly X naught. In this case, 1 meter. Okay? You can say thus, in this case, that, and I want to say this, let me just, okay, so one way to say this is that since I measure, so if I measure particle A, I can predict with unit probability the position of particle B. Right? Moreover, there's an important point that I mean to emphasize here. There's this notion of without disturbing, right? So that's an important point here. And what do I mean by that? What Einstein meant by that was that I can't affect where particle B is going to be by measuring A. And how did he insist that that must be true? So if A and B, so in this case, A and B are time-like separated. Which is to say, no signal, once I measure where particle A is, I can't in any way affect where B is because B is outside my light cone. Okay? So in the reference frame, say where they're at simultaneously, you know, here's A and here's B, he's in elsewhere. And in any other reference frame, they're time-like separated, right? So A and B, I can't affect where B is because B is, in some reference frame, simultaneous with me, but just at a different position. So there's no way that B is not inside my light cone. So I can't disturb it. That's the no disturbance assumption. That there's no way that a signal can get from A to B faster than the speed of light. I mean, unless it was coming faster than the speed of light. Okay. So that's crucial to the argument. So the fact that I can predict where B is with unit probability, and because B is time-like separated from A, it must be the case that B had a definite position. I just didn't know it. Because I can measure A, I see it here, and therefore I know exactly where B is. And so if someone measures B, I know what they're going to find. I know it. They're going to find my position plus 1 meter with unit probability. That's what they're going to find. They're not going to find a random result. They're going to find exactly, if I found it at 0.2 meters, I know they're going to find B at 1.2 meters. Therefore, since I can predict where B is going to be found with unit probability, and the fact that they're going to find it can't in any way be affected by me because B is outside my light cone, the argument is that the position of B is an element of reality. I could have done it the other way around. I could have measured B and then I would say A was an element of reality. Okay, so that's one part of the argument. We haven't got to the paradox yet. Yeah?
So this is kind of like what we were talking about the other day where, you know, we had to take a spin, and if I measure spin up, using this, somebody has to measure spin down.
Right,
okay.
Exactly. And we're going to talk about that in a moment.
Okay.
So the thing about this state, so this state, the EPR state, notice that the EPR state can also be written in the momentum representation. Okay? So let's do a change of basis. How do we do that?
Fourier transform? No.
Right. It's Fourier transform, and that's equivalent to inserting a complete set of momentum bases, right? So I can write this in, I'm going to insert two resolutions of the identity. One for A, and one for B. Right? So all I did is I inserted a resolution of the identity. And this is e to the I, P, A, X, k over root 2 pi h bar. And this is e to the I p prime xb plus x naught. Right?
X A plus X
Uh,
just because of the, you know, the position. of-
Yeah, I should actually, so let's just actually leave it like this. I don't call them A and B here, they're just X. Right? So this then, I can write this as the integral dp prime, and then there's another square root of 2 pi h bar here, there's an h bar over there. So this is integral dx 2 pi h bar. There's just a chalk. E to the I p prime x naught. Let me bring that outside the integral, sorry. Integral dx over 2 pi h bar. I p plus p prime x over h bar, and then I got p a p prime. Okay, and this integral over x is a delta function. So, in the momentum representation, the EPR state is, I can integrate this becomes integral over p, e to the minus I p x naught, p a minus p b. So once again, we have an entangled state that shows a correlation. If you measure particle A's momentum and find P, you will find the momentum of particle B is minus P. They're anti-correlated in this way. Okay? So this two particles, if you measured its momentum, here you would find, if you found it was going like this particle would be going like that with equal and opposite momentum. You don't know what the momentum is going to be. It's completely random. But once you find it, you find whatever it is, 1 kilogram times a meter per second. This one is minus a kilogram meter per second. Okay? So this is also correlated. Now, so notice that this state is simultaneously an eigenstate of two collective operators. Note, if I look at the sum of the position of particle A and particle B acting on this, I'm sorry, the difference in their positions, it's always x naught. Right? No matter, it doesn't matter what position, but this is, it's an eigenstate of that difference operator. And it's also an eigenstate of this, with eigenvalue 0. It's a simultaneous eigenstate of those two observables, but that's okay, these commute. In fact, they have a complete set of common eigenstates.
29th Thursday.
All right, so note here that the same thing is true. So what that says is that if I measure the momentum of particle A, I can predict with unit probability the momentum of particle A. I'm sorry, particle B. Right? And what, by the EPR argument, and since they're outside the light cone of each other, and my action cannot signal in any way to particle B, what EPR argue is it must be the case that the momentum of particle B is an element of physical reality. Okay? And thus the paradox. Because what this says is that, well, if I had measured position, I would have been able to predict that. Therefore, it must have been the case that the position was always definitely something. I just didn't know what it was, and when I looked at it, I found out what it actually was, objectively. The same thing is said about momentum of particle B. Therefore, what they would say is that the position and momentum of particle B are both elements of physical reality, which violates the uncertainty principle. Let me just finish the thought. So their argument is that that both the position and the momentum actually have objective reality simultaneously. And when you look at them, you find some, whatever it was. And the only reason that the position outcome and momentum outcome are ever random is because you don't have complete information. But the information exists in the real world. Hence the paradox. That's the EPR paradox. So, Zeke, you had a question?
I'm sorry, but like, you know, these X minus A, X minus B, P, PSA, I mean, like, does that kind of say that we're doing the measurement at the same time, though?
No.
Okay.
So that, of course, I mean, this is, of course, the flaw with the EPR argument. You either measure position or you measure momentum. You're not measuring both at the same time. If I measure position, I will find a certain outcome for the position of particle A. And then it's for sure true. I could know what the outcome will be for the measurement of position B. Because it is an eigenstate of the position separation, I know for sure that that's going to be. Okay. Right? Or I could have measured momentum. If I measure with some kind of momentum detector, the momentum of particle A, I'll get some outcome. And then I know for sure what someone who measures the momentum of particle B outside my light cone will find. They will find it moving with exactly the opposite momentum that I found. If we later compare our lab notebooks, we will see always that. But we did either a position measurement or a momentum measurement. We didn't do both.
Well, I mean, not both position measurement, but like XA, say my XB. Does that, I mean, that doesn't mean I took measure position A and measure position B at the same time. That's what
I could. They're two different particles.
But I don't need to tighten this correspond.
That's right. What I could say is I measure particle A, and I find its position, and I haven't yet measured B.
Okay.
Right? And then I say, hey, Z, go measure B. I know what you're going to find.
Okay.
I know because my state was prepared in the perfect EPR state, and you're going to find the particle is at 1 meter, because I found mine at the origin. Okay? Because they are always eigenstates of the separation operator. Okay? So it's true. So, you know, Bohr and Einstein argued about this afterwards, but it's, I mean, I think it's a very compelling argument, right? What it says is that, you know, I know what you're going to find with 100% probability. Therefore, that must have been, it had that property. It's not that I made that property emerge by me measuring A. I didn't make the property of B emerge by measuring A, because B couldn't have received a signal from me. B is outside my light cone, as long as you're measuring them. I mean, of course, if you measure them too late, then of course, ultimately, you know, B could be within my light cone. But as long as you do it quick enough, there's no way that what I do could in any way affect you if we believe in Einstein locality. That no effects travel faster than the speed of light. And similarly for, you know, so sure, I didn't measure momentum at the same time, but the same thing is true. So it must have been that both of these things really, they have objectivity. Right? I mean, it's a very compelling argument, I think. So this kind of bubbled around for about 30 years. It was a little less than, I think EPR was 1935, I'm not sure, maybe it was 38, I don't remember. But in 1964, which is, we're at the 50th anniversary, this was 2 years before I was John Stuart Bell. So, John Bell was a particle physicist, particle theorist, worked at CERN, and revisited, you know, there were, at this time, the questions of the foundations of quantum mechanics, 30 years after EPR, you know, it was, no one was thinking about it. It's like, it was the shut up and calculate mentality, you know. We know quantum mechanics works. We can predict, you know, there was all of these, the standard model was being illuminated in particle physics, and everything was, you know, quantum mechanics was working. So the foundations wasn't something that people thought was a serious endeavor for physicists. It was for fuzzy-headed philosophers where physicists look their noses down. But Bell revisited this problem. He wasn't the only one, there were others. And tried to ask the question, is there a quantitative test that distinguishes quantum mechanics from local hidden variable theory. Okay. So EPR said there must be local hidden variables because I can show you that there are elements of reality, position, momentum, and when you're seeing things randomly, it's because there are local hidden variables. And it was, at this point, a somewhat philosophical argument because, of course, as we said, we can't actually do measurement of position and momentum simultaneously as projective measurements. So John Bell, I mean, he knew about the Bohm theory, the Broglie-Bohm, and that there were non-local hidden variable theories. But the question is, if I have a hidden variable theory, and if it is consistent with quantum mechanics, must it be non-local? Or do there exist local hidden variable theories that are completely consistent with quantum mechanics? Okay? Can I rig up some Rube Goldberg machine with bowling balls rolling down the hill, striking the match, making the coyote jump off the cliff, that's going to rig up the same thing as quantum mechanics, but it's all local. So to do that now, what he looked at as the EPR state is not a physical state because it's not normalizable. Okay? So the EPR state is a kind of a Gedanken experiment, but we can never make the exact EPR state. We can make a good approximation to the EPR state, but we can never make the exact EPR state. It's not normalizable. It's like you can't make a position eigenstate, right? There are other issues about the EPR state, which I'll come back to maybe at the end. Actually, there is a local hidden variable theory for EPR state, but that's another story. Just put that aside for the moment, because that's a positive data function. But anyway, I just mumble that, so no point really. But at the time, David Bohm had looked at a equivalent version. So the Bohm version, David Bohm of EPR, with spins instead of, so we'll talk about spin degrees of freedom rather than position and momentum. Okay? So what David Bohm considered, which is also now called the EPR state, but for the moment I'll call it the Bohm state because David Bohm deserves some credit for this, amongst other things, was to consider the following entangled state, the kind that we talked about last lecture. So this state is spin up along the z-axis for particle A and spin down along the z-axis for particle B. They're at different positions, so I can distinguish that. Or the other way around, with this minus sign in between. Now, explaining why that minus sign is important in a moment. Okay. So this state is also an entangled state. And again, it has properties that you can do measurements on one particle and predict with certainty what the outcomes will be when you do measurements on the other particle. Okay? So in this case, if I measure spin A along the z-axis, I get plus or minus 1 as my eigenvalue. And for B, minus plus 1. That is to say, if I measure spin A, spin B, or let me look at another way around. Let's write a table here. A, B, okay? If I measure sigma ZA, sigma ZB, if I get plus 1 here, I get minus 1 here. If I measure minus 1 here, I get plus 1 here. Right? Always. Each one of these happens with 50% probability. So I don't know whether I'm going to get spin up or spin down along Z. It's completely random. But if I have my spin here and I measure it, I can predict with 100% probability what B is going to see. Okay? Now B doesn't know, Bob doesn't know what he's going to see. He's going to see either up or down. But at the end of the day, we call each other up. Yo, Bob, I got plus 1. I bet you got minus 1. How did you know? Well, because we were at this entangled state. Right? So they both see random results. If there's a series of this, they'd see a series of random bits. Up, down, 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 up, down, 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 up, down, up. And the other one would see exactly anticorrelated thing, right? Okay? Now, one of the things that's special about this state is that it has, not only is it anticorrelated in Z, it's anticorrelated along any axis. Now how do we see that? So this thing is an eigenstate of, if I look at the total Z spin along the Z axis, and that's the total spin component for the sum of the two particles, that on the Bohm state, this is 0, right? What about the total x? Let's look at the total spin component along the x-axis. I won't put in those tensors there because it's too messy. That's what it is, though, right? How do I apply this operator to the Bohm state? Well, so that's, whatever this is, A bar 2, whatever root 2, that's sigma x A up along A. That's the first term. Right? That's applying sigma x to that. And then I have it on the B. X. So all I did here is I applied sigma x to the first guy plus sigma x times the second guy. Okay? Okay, now a little bit of memory. How do we apply sigma x to spin up along z?
Split z up into x plus x.
We could do that, yeah. We can make this in the x basis, or we can remember that sigma x, I mean, this is just, there's lots of different techniques. I want to remind you of many different ones. Standard thing is think about sigma x in raising and lowering operators, okay? It's a little quicker. So sigma x is sigma plus sigma minus. And sigma plus on up is 0, and this is down, okay? So sigma x turns up into down and down into up, and the same, okay? So this then is down along A, and this is up along A. I mean along Z for A. And this is up along Z for B. And this is down along Z for B. And thus, what is this equal to? Well, there's this minus sign here, so these terms cancel. There's a minus sign, and these terms cancel. So this is 0. And the same thing is true, sigma y is h bar 2I sigma x minus sigma. No, yeah, sigma, sigma is y, sorry. And the same thing is true here. Sy, acting on the bone state, is also 0. The total spin. Okay? So what that means is that S squared on the bone state, the total spin of the particle, that's Sx squared plus Sy squared plus Sz squared, acting on the bone state, is 0. This is what, so the bone state is a total spin 0 state. And this is for reasons that you may have learned and we will review next semester. This is known as the spin singlet. Could be distinguished from the spin triplet, which we'll review next semester. So, with this, you can, with a little bit of work, we can show, for example, that with a change of basis, the bone state, for example, is equal to spin up along x correlated with spin down along x minus spin down along x correlated with spin up along x for particle A and particle B. Okay, so that means that the same thing would be true if this were x. So if you measure the spin along the x-axis, you're going to get a random up or down, but they're always anti-correlated. So that means if I measure spin A along the x-axis, say up, I can call Bob on the phone and say, hey Bob, measure your spin along the x-axis. I know what you're going to get. Okay. Yeah.
So the EPR philosophy, did they think that it was plus or minus one or minus one plus the whole time? We just didn't know and take the measurement, or no?
Yeah,
Okay,
exactly.
okay.
So the EPR philosophy, well, we'll come back to we'll say this. Let me just say one last thing and then I'll connect that to EPR.
Okay.
So I should say that it's generally the case. You could show, because this is a spin singlet, this is an eigenstate of spin along any axis. Zero, which means that they're anti-correlated. You know, if I write this, it says that n hat sigma dot A on the bone state is minus the value for measurement along the same axis for particle B. Right? So if I come back to this chart once more, I can measure this along any axis. X-axis, the y-axis, the z-axis, the axis at 45 degrees, and it'll be either up along that axis or down along that axis. And I can tell Bob, measure along that axis, put your Stern-Gerlach apparatus with your gradient along that axis, you're guaranteed to find anti-correlated. They're perfectly anti-correlated along any direction. Okay?
So even if you prepared it in that up and down Z state, it doesn't matter when you take your measurement.
So this is a representation.
Okay.
Okay, you prepare the bone state. So the bone state is a state of, so we imagine we have two particles that are together in a spin zero. They fly apart. This spin singlet is made up of these two spin 1/2 particles, and somehow this thing decays, conserving the total spin angular momentum, and this flies apart. Okay? So there's a particle here, and a particle here. I'll call this one A, and this one B. This started off in the bone state. Okay? Now I have a Stern-Gerlach apparatus which I can orient along any axis I like. And for A and for B. And they can measure that, and they're going to get up or down. If they have their gradients along exactly the same direction, then they will be anti-correlated. If this guy goes up into that detector, the spin, goes into the up detector. This guy, if it was oriented along the same axis, would absolutely go down. Okay.
So that's just representation and spin up and spin down on Z. It's not,
Right, but
okay.
but it's equally well written
Okay.
as this.
Okay.
In any basis, it looks like this. Okay? So it doesn't have a definite spin up or spin down value. So this is the bone version of the EPR argument. It says, if I measure spin A along Z, then I can predict with 100% certainty the spin B projection along Z. And if spin B measurement is outside my line cone, I cannot affect the outcome of B measurement. Therefore, the spin projection along Z of particle B is an element of physical reality. By EPR. Okay? Alternatively, same holds for a measurement of spin along X. Implies spin projection along Z, or I'm sorry, along X of B is also an element of physical reality. But sigma x doesn't commute with sigma z. So that violates the uncertainty principle. It says I can assign definite outcomes to both an x projection and a z projection. In the same way that EPR argued, I can assign elements of reality to both position and momentum. Now, of course, you don't measure both x and z at the same time. But the EPR argument is that since I can predict what you're going to see with 100% probability, it must have always been that way, because I couldn't have affected what you were going to see. And since it doesn't matter that I do these as two separate measurements, since I am not going to affect what you're going to see, it must have been the case that it was, the spin was always up along Z or down along Z. You just didn't know which one it was. Okay? It's a compelling argument. All right, so given this property of the Bohm state, what did Bell do? So what Bell did is to say, let me consider, define a local hidden variable theory. Okay. Such that there is, so lambda is a hidden variable. We don't know what its value is because we don't have a complete description of what's going on inside the spin. But there is something inside the spin that tells it whether it's up or down along a certain axis when it's measured. It's inside the spin and it's going to tell us what it interacts with the apparatus in just the right way. There's objective deterministic reality, and lambda is a variable or set of variables that governs that. Okay? So, let A, E sub n lambda equal the value of the spin A along axis En. Okay? So if you measure the spin along a certain axis, there are some set of variables that tell you this is the whole state of the system. Okay? It's everything about the system. Everything. So it includes psi and whatever other hidden variables there are. This can be plus or minus 1. Okay? Let me call this, and then there's B. B measured along some other axis. I don't need notation here. Okay, N prime. Okay, so there are objective values. These are in the world. They're attached to the spin somehow. When you measure it, you just find out what it actually was. Okay? And they depend on lambda, but they're local hidden variables in the following sense. That the value that you find, or the value attached to spin A, is independent of the axis I'm going to look at it from B. It doesn't, what I measure along A in no way affects the outcome of B. They may be correlated, but there's a difference between correlation and causation. Okay? So local invariable this is to say the axis along which Alice measures does not affect the value B will find. This is the whole idea of the Einstein causality. What I do can't affect what you're going to find because I'm outside your light cone and therefore I can't affect you. Okay? Now that's different from correlation. Okay? Now, I have two colored chalks here, a red and a yellow. Okay? I'm going to give one to Zeke. So come over here. Don't tell anyone. Okay? And Jesse, you're going to get it. Okay. Okay. Zeke, what color does Jesse have?
The opposite of mine?
What color do you?
Oh, pink?
She has pink,
Okay.
right? So you can predict with absolute certainty, right? But you didn't affect what she had. But they were correlated. They were correlated because we saw the preparation, and they were correlated because they were local with one another at some point. They were born from my motherly hand and given to you. You can show them that. But it's not that the act of seeing that it was yellow caused hers to be red. It couldn't have. There's no effect there. They were just correlated to begin with. And the idea of EPR is that that's the way the world is. The spins are correlated, and they can be correlated in all these different ways, but there's no action, and therefore, since there couldn't have been action, and since, or there couldn't have been effect, and since you can predict it, it must have been that way all along, and in fact, for the different possible measurements you could do. Okay? We're going to go to 11. That's okay, because what the heck? You have patience. Let's go back to the back border here for a moment. Let me just say a few more words about this. So the thing I just did with the colored chalk, we could have done is something to make this, where, let's say there are two marbles. They're prepared always together inside this, Easter egg. You crack it open, you send one marble here, one marble there. Now let's suppose the marbles are coated with something when I put on my 3D glasses on them. So I can choose to look through the, one eye or the other. And depending on which eye I look through, I'll see a certain color of the marble, right? So it's not like I could do a measurement on this thing, say with the filter, right? And depending on what I see, it could be always correlated. So I choose to look through the left eye, it'll be green, and this guy will always be, if he looks through the left eye, he'll always see, what's opposite of green? Red. It's Christmas after all, right? Or if he looks through the other eye, he'll see orange and blue. So they're always correlated, green with red, orange with blue, right? Now, of course, if they look with opposite eyes, they don't see these correlations. But you can create a situation classically where you can choose to do measurement as well, right? All right. So, Bell said, fine. This is the minimal assumption that there is an objective reality. The objective reality is dependent on a hidden variable that, or whatever variable, some of which are hidden and some of which may not be hidden. And what I see is dependent only locally on what I measure and can't depend non-locally on what anyone else measures. Okay? So, I guess I will put this just because I think we'll be confused otherwise, so I'll call that A and B. Those are the two axes. All right. So now let's look at correlations. Okay. So suppose that we're going to look at, as we saw, that those two colored trucks were correlated. Okay? And the question is, are those correlations, can they be explained by local hidden variables? That's really the question. Can the quantum correlations associated with entangled states be explained by local hidden variables? So, for example, let's consider that there are two. I want to look at the average value of products. So Alice is going to measure her spin along direction N and B along N. Okay? So in the local hidden variable, if I want to know what the average value of this is. In the local hidden variable theory, that would be, well, there's some value that A finds along, and you multiply it by whatever B finds along his axis. But I don't know what lambda is. So I have to average. where this is a classical probability distribution. Okay. That is to say, lambda is the missing information. If I knew what lambda was, I would know exactly what I would find. But since I don't know lambda is hidden from me. Nature has hidden it. It's in principle accessible, we just haven't found it yet. I have to, when I look at the average value of this, I have to average over the probability distribution of possible lambda values. Okay? That's a local hidden variable theory. That would say that there are random outcomes. This is a stochastic variable who is sampled from a probability distribution, classically. Now, quantum mechanically, we know how to calculate this. This is the expectation value of sigma n A. This is sigma n A. Okay. So this is the question. Is there a possible probability distribution such that I can rig it up that it gives me the same correlations? All right, so to do this, Bell considered the following Gedanken experiment. Okay, so let's have our spin singlet. And the two particles go off in the two directions, okay? And now I have two analyzers. Alice can analyze along, she has a choice. She has her analyzer. She can choose to analyze along some direction A or some other direction A prime. Okay? So she has a choice. She has a certain apparatus. She can orient it. She has these two choices. So she'll either see spin up or down along this direction if she measures along this axis. But she might choose to measure along that axis. And when she does that, she'll either find up or down. And Bob similarly has whatever axis. He has two different axes. They might be the same as Alice's or not. I'm not going to say for the moment. I'm just going to say there's an EB and an EB prime. So Bob has also a circular apparatus on his side of the particle he gets, and he can choose to analyze it along this axis or along that axis. And okay. So now I'm going to talk about a particular form of correlation that was first described, which is a generalization we'll go down, which was known as the CH-SH inequality. And CH-SH inequality is a form of Bell's inequality. It's not what Bell originally wrote down, but it's more amenable to experiments. The CH-SH stands for Clauser, Horn, Shimoni, and Holt. But everyone knows it as CH-SH. So, what did they consider? Well, they considered the following quantity, which call S. S is equal to sigma A along axis A, sigma B minus sigma B prime. Actually, this doesn't really matter, plus sigma A prime, sigma B plus sigma B prime. Okay, so it's a particular set of correlations, right? This is the average value of this is equal to the correlation like this minus the correlation like that. I'm sorry. Plus the correlation like that. Plus the correlation back. Okay. So it's, the experiment is that you do this many times. Alice and Bob kind of randomly decide whether they're going to analyze along the A or the A prime axis, B or the B prime axis. They get either plus ones or minus ones. They get back together, they fly back from their spaceships on the other side of the Andromeda galaxies, and they compare notes. And they say, okay, on this run I measured along A, and I measured along B prime. So we multiply our values together, it's either plus one or minus one, and that corresponds to this one of these guys, right? And then in the next run I did this, and you do this many times, and then you average all the times that Alice measured along A and Bob measured along B, that corresponds to this, you average all those results. And every time, etc. Okay? All right. Why does this matter? What does this have to do with it? Well, if this were a local hidden variable, theory, then there is some value of these guys, all these guys, we just don't know what they are, right? So for local hidden variable theory, this is equal to etc. Right? And each one of these things takes on the value plus 1 or minus 1, right? So, we don't know what it is, but it is something on its way to the detector. Okay? So, in the local hidden variable theory, each one of these things is definite value simultaneously. All of these exist simultaneously. We just don't know what they are. Do you see what I mean by that? So this is either plus 1 or minus 1. I just don't know what it is. And the value of lambda would tell me which one it is, but I just don't know. This is plus 1 or minus 1. I just don't know what it is. This one is plus 1 or minus 1. I just don't know. This one is plus 1 or minus 1. Okay? So, in some run of the experiment, it might be the case that the lambdas dictate that for some run, this is true. Okay? They're both plus 1, right? So if that's true, this is 0. In that case, S is equal to 2 sigma A prime sigma B. Right? Because this is 0, and this is equal. So that's twice whatever that value is, times sigma A. For another run, for some run, some other run, they were opposite. Okay? In which case, this is equal to now, right? Because this is 0, and this is equal to minus that, so it's that. So in any run of the experiment, the value of S is either plus 2 or minus 2. According to the local hidden variable theory, in any run of the experiment, if you did these things, S is either plus 2 or minus 2. Okay? So that means, according to the local hidden variable theory, this is equal to the integral over the probability distribution, S for a given value of lambda. And since this is plus or minus 2, that means, and this is a probability distribution, this thing is bounded. S, the average value of S, must be between 2 and minus 2. It can never be bigger than that. This is Bell's inequality. This is the CHSH Bell inequality. Says that if you did this experiment, now of course, in any one of the experiments, you either measure a pair. You can never measure all things at once. But in the philosophy of local hidden variable theory, there was a value. You just didn't know what it is. Even if you didn't measure it, it had that value. And it had to have had it because I can predict it and I can't affect you. So it must have been that way all along. But you do the measurement in pairs, right? You do some of these, some of these, some of these, some of these. You do them over and over and over again, and then you multiply all these values together, then you average it. Okay? So let's see what quantum mechanics says. So, what is true is that if I look at that correlation. So if this were, say, the z-axis, this would be sigma z, right? And then it would be -1. If this were the x-axis, it would be sigma x, and then it would be -1. But it could be any axis. You can calculate this, it'll be your first homework problem next semester. And this is equal to this. Okay? So if they measure along the same axis, they always get anti-correlated values, right? If they measure along different axes, well, then it's not perfectly anti-correlated. So if you measure along x and Jesse measures along z, then they're not perfectly correlated. Okay? In fact, if they're orthogonal, it would be no correlation whatsoever. But if, you know, if they're close to one another, they're very anticorrelated, etc. Okay, this is just quantum mechanics tells you this. So, let me get my notes here, because this is the part I never remember. All right. So, when you now look at that expectation value of this becomes an operator now. Okay. And I look at that expectation value, what I get is the following. I get minus EA dot EB prime minus EA dot EB plus EA prime dotted into EB prime plus EA prime dotted into EB for all those terms. Okay. Now, yeah, sorry. So now, let us just take a particular case. Let's say that these different measurement analysis directions are all in a plane. Okay? Consider this a particular case where, so here's EA, and here's EB. And I'm going to make it such that they're separated in the following way. So that's just a particular case of measurement directions that are separated in angles this way, okay? So that measurement B prime bisects the two possibilities that Alice has, and possibility A prime bisects the two possibilities that B chooses, okay? That's just some choice. Okay? So when you do that, what you find is that the quantum mechanical average value of this value S is the following, is 3 cosine theta minus 3 cosine of 3 theta. That's just a little bit of trigonometry. Okay? So for example, if theta is small, much less than 1 radian, then this is approximately 1 minus theta squared over 2 minus 3 times 1 minus 9 theta squared over 2, which is 2 plus 3 theta squared, which is greater than 2, which violates Bell's inequality. In fact, you get maximum violation when theta is equal to 45 degrees. Then the average value of this quantity is 2 root 2. It's maximum possible value.
And you're still only measuring 2 at a time?
Yep.
Okay. How would you get more than 2 total spin, though?
Well, of course, so this is the quantum mechanical value, right? It's that, I mean, so it's just this question of whether you get, it was only because I assigned simultaneous definite values to these things that I was able to show that it was either +2 or -2. But you don't assign simultaneous values. You assign definite values to a pair of experiments, but in another pair of experiments, I can have something different. And in that other experiment, it might be the case when I multiply those things together, it's greater than 2. It doesn't have to be that for some run, I can't talk about this because I either measure B or B prime. I can't talk about this really. This is only true if they had the values. So this is what we call a violation of Bell's inequality. If you sketch this as a function of theta, what you find is that this is -2. Look at this average value. What it generally is, a function of theta, looks like this. So this is 45 degrees. This is 135 degrees. This is 2 root 2. Let me make a few comments here. What this profoundly says is that there is no possible way to say that there was a local hidden variable, that the spins were either up or down along all these axes. I just didn't know what it was on its way. There's no way. Because it always comes out to be ± 2, those things. And if it goes beyond that, there's just no consistent theory that says that. And what is just profound about this is that we can distinguish different philosophical pictures quantitatively. That's amazing. Now, what do we say about this then? Well, there's different approaches. One way, what people say, some people, the wrong people, is that what this proves is that quantum mechanics is non-local. Because they don't want to give up the sense that things are realistic. So they want to say that the reason when I measured my spin along the z-axis, I'm actually physically making the spin do something, and I'm physically affecting Adrian's spin non-locally, faster than the speed of light, there's somehow, I'm making something happen to his eye. There is an effect. But this, in my view, conflates the question of correlation with causation. What Bell's inequalities tell us is that quantum mechanical states are correlated in some sense in a way that can't be described in terms of a classical local invariable theory. But it doesn't say that there's causation. There's nothing I can do. This is another, this is, I think, an important and interesting piece of also history. There's nothing I can do to signal to Adrian what I measured, even though we're perfectly correlated. So, we did this experiment with the yellow chalk and the pink chalk, right? There's nothing that you could signal to Jessie, but she had her pink chalk, right? And there's no Morse code you could send to her by what you choose to measure. You're going to see a string of random bits in this, doing this kind of EPR experiment. It's just afterwards, if you looked at those bits, you would find they were correlated. But there's no measurement you could do that could in any way signal through entanglement. Entanglement can't be used to send signals non-locally. Now this was interesting because, after Bell, 1964, again, probably was rattled around, I don't know the history exactly, but there wasn't a lot of attention paid to it, it just kind of languished. Till sometime in the 1970s, when there were a bunch of out-of-work physicists in Berkeley, California, who, it was sort of the bubble after Sputnik. There was a whole bunch of physicists, everyone was like, go into physics, we can't, the Russians are coming. And then there was inflation, recession, who knows what happened in the 70s, and all these guys, I think they were mostly guys, out of work. And they, this was the early 70s, and in Berkeley it was, the end of the hippies. And they were into notions of ESP and being able to, could I affect things through my mind, they had Bell, and there was all this thing. So about what does this really mean? People were thinking at that time that, yes, you could use entanglement to communicate faster than the speed of light. And they were the first people who started to do experiments with those in cars. So John Clauser, who I met when I was a student at Berkeley, because I was a PhD student there, he's a really interesting guy. He's like an experimentalist, the kind of guy like, put his tongue on the thermocouple to know if it's working or not. He did the first experiments on this kind of stuff. But with others he was working with, they were really trying to see, could I communicate faster than the speed of light? And it was kind of like perpetual motion. We knew that this kind of violated physics, but we didn't know why. And the process of trying to unravel why entanglement couldn't be used to communicate faster than light helped us to more deeply understand some of the foundations of quantum mechanics. For example, you may have heard about the no cloning theorem. Have you ever heard of that? That came out of this question of why you couldn't communicate faster speed of light. But you know, the thing is that we should look at here, of course, if I think about, just to conclude with this last bit here, that you should always keep in mind, quantum mechanics tells us what, so here we had, you know, we had this spin saying that, and it was in an EPR state, or a Bohm state. If I ask you, what is the state of particle A? How do you find it? So this is a joint state of particle A and B. Now, whatever measurement Alice does with whatever detector, according to quantum mechanics, her measurement outcomes, the probabilities that she will find certain outcomes are defined by the density matrix that she, or the density operator that she assigns to her spin. What is that?
It's the marginalized one.
Exactly. It's the marginalized density operator. So what you do is you do the partial trace over B of the joint state. And what is that in this case? Well, you know, there's a state.
Is it completely mixed like that?
Exactly. This is a completely mixed state. It's 50% up and 50% down along any axis. I see a random result. I'm Alice. What's Bob's state? Exactly the same. Both of them are completely mixed. They're random bits, but they're perfectly correlated. And this is the bizarre thing about an entangled state. An entangled state is perfect knowledge about the whole and complete ignorance about the parts. So even though they're perfectly correlated, their parts are completely random. And this is what makes, in some sense, quantum mechanics different, because he's one of the key things. But you shouldn't think that what Bob is doing is affecting Alice, or vice versa. It's just that they were correlated. In the same way that the pink chalk and the orange chalk were not affecting one another, they were just correlated. But in that case, they were correlated in a local, hidden way. In this way, they're correlated. I would, if you want some fun Christmas reading, there is a great little book by John Bell that's worth reading. It's really a lot of fun to get a lot of deep insights into it. And the 50th anniversary of Bell's famous Inequalties. It's good to look at it. All right, folks, have a great Christmas break. I look forward to seeing you next semester. We'll have lots more fun. Take it easy.